So in simplex method, let's say we have an objective function that is z equal to 5x plus 5x1 plus 3x2, and we have to maximize it, which is subject to constraints 3x1 plus 5x2 less than equal to 15 and 5x1 plus 2x2 less than equal to 10. And what follow are the non-negativity constraints. If we have to solve this, we can use three methods. One is the graphical method. The second one is the algebraic method. And the third one is the simplex method, which is also known as simplex algorithm. And we'll be solving this with simplex method. And the good thing about simplex method is it only gives you basic feasible solutions and progressively better solutions. Now, what this means is that if the objective is to maximize, then with each iteration, the value will increase, right? So we begin the simplex method by making a tableau, which is as follows. Before we proceed with this tableau, we have to make the inequalities. We have to introduce slack variables. So 3x1 plus 5x2 is less than equal to 15, but it can be made equal to 15 if I introduce an amount that is just enough to make it equal. Similarly, for the second constraint, I can introduce x3, x4 in this case, where again x3 and x4 are greater than equal to 0. These are called the slack variables. And so in the tableau, what we make is like so: x1, x2, x3, x4. We have the RHS, and then we have something called theta. Now, here we have four variables, two constraints. So we can solve these equations in 6 ways. But the solving, we won't be testing these 6 ways because that is done in algebraic method. But in simplex, but the solving remains the same. That is, we consider 2 variables at a time. 2 variables. So we begin by taking these variables, because start by assuming these slack variables as basic variables. So they enter the basis. And if we represent these constraints in the tableau, it should be 3, 5 plus x3 equal to 15. Similarly, 5, 2 plus x4 equal to 10. And here come the coefficients in the objective function. So the objective function is 5x1 plus 3x2. And as you can see in the objective function, the slack variables don't have any contribution whatsoever. So the coefficient remains 0 here, and we start by solving. We have something called Cj minus Zj, which is this value minus the product, the dot product of this vector and the corresponding vector. So this value here would be 5 minus 0 into 3 plus 0 into 5. That would be 5. Similarly, this would be 3 minus 0 into 5 minus 0 into 2. That would be 3. Here it would be 0 minus 0, that's 0. And similarly, here it would be 0 minus 0, that's again 0. In this case, for RHS, you do what's called a direct dot product. And here it would be again 0 into 15 plus 0 into 10. That's again 0. So anyway, that marks the end of the first iteration of Simplex. And now we have to move forth and do it. We extend this tableau again, and now we decide which variable enters. Because at this stage, we've got solutions to the objective function. X3 is equal to 15. X4 is equal to 10. But they don't appear in the objective function. Hence, the value of the objective function remains 0. Now we have to solve for x1 and x2 because the value of the objective function depends on these two decision variables. So we have to attempt to bring these decision variables into the basis of the problem. Now, how do we decide? So the rule is that the highest Cj minus Zj enters, and where does it enter in this column? We have to decide. Now, how do we decide? For that, we have a parameter called theta, which is RHS divided by the corresponding value. So in this case, it would be 15 by 3, that is 5. And in this case, it would be 10 by 5, that is 2. And the rule is that the highest Cj minus Zj enters and the lowest theta leaves. So if we look at this, the corresponding element would be 5. And entering variable would be x1. So what we get now is x3 and x1. And basically, if you see, whatever the variables we are solving for have an identity type column matrix. So in the first iteration, we solved for x3. It had a 1, 0. Likewise, x4 had 0, 1. So the basic variables must have an identity column. So x1 is having 3 and 5. We have to attempt to make it 1, 0. Because x4 leaves, it's actually 1, 0 in place of x4. So to make this 1, we divide the whole row by 5. So that will be 1 by 5, 0, 1 by 5, 2. Now, this element here should be 0. But how do we make that? This row minus 3 times this row. This row minus 3 times this row would be 3 minus 3, 0. 5 minus 6 by 5, that is 25 minus 6, 19 by 5. 1 minus 3 times 0, that is 1. 0 minus 3 times minus 3 by 5. 15 minus 3 times 2, that is 6, 9. And now we calculate the corresponding Cj minus Zj again. Here we have the coefficient of x3 is 0 and coefficient of x1 in the objective function is 5. So if we calculate Cj minus Zj, 5 minus 0 minus 5, that's again 0. So basic variables will always have, see x3 and x1 in this case are basic variables. So Cj minus Zj corresponding will be 0. It could be seen here as well where x3 and x4 were basic and the corresponding Cj minus Zj values are 0. Now, if we solve Cj minus Zj for this, it would be 3 minus 0 into 19 by 5 minus 2, that is 1. Similarly, for x4, if we see 0 minus 0 minus 1, that would be minus 1. And here it would be 0 into 9, that is 0, plus 2 into 5, that is 10. Now, only the non-negative highest value enters for Cj minus Zj. So in this Cj minus Zj, 1 is the highest value that enters. Now you have to decide which variable leaves. Ideally, since we are solving for x2 and x1, x3 should be the one to leave. But we'll see. So out of this, which one will leave is something we have to decide. So 9 divided by 19 by 5, that would be 9 into 5 by 19, that is 45 by 19. Similarly, this would be 2 divided by 2 by 5, that would be 5. So clearly this will leave because 19, this is 2 point something and this is 5. So the minimum value leaves. And so this becomes the pivot element. Now we've come to the third iteration of the simplex algorithm. And again, the aim is to make this 1 and 0. But how do we do that? So we make it 1 by dividing the whole row by 19 by 5. So that becomes 0, 1, 5 by 19. This becomes minus 3 by 19. This becomes 45 by 19. Similarly, we have to get a 0 here. So 2 by 5 minus 2/5 of this row will make it a 0 here. 1 minus 2/5 times 0 is 1. 0 minus 2 by 5 times 5 by 9 is minus 2 by 9. 1 by 5 minus minus will become plus. 1 by 5 plus 2 by 5 times 3 by 19. That should be 34 by 95. And this would be again 2/5. So 2 minus 18 by 19. 38 minus 18 by 19. 20 by 19. And now we calculate the Cj minus Zj values. It should be 5 minus 3 times 0 minus 5, that is 0. Again, x1 and x2 are basic, so automatically the Cj minus Zj values become 0. This should be 5. Well, x3 has a coefficient of 0. So 0 minus 15 by 9. Plus 10 by 9. So that would be minus 5 by 9. Similarly, here it should be minus 9 by 19. So basically minus 45 by 19 minus 45 by 19 minus 45 by 95 minus 34 by 95. 45 by 95 minus 4 into 5, it is 95. So similarly, we would be having minus 125 by 95 with a value of 45 into 3, that would be 135 divided by 19 plus 100 by 19, that is 235 divided by 19. Now, as we can see, there is no variable that will enter anymore. because these values are negative. Only non-negative and the highest value can enter. This is a basic variable. So these have zero values. These are negative. So this means that the simplex algorithm will now terminate. Simplex terminates. Now we can observe a few things from here. If this is the first iteration, this is the value of z. This is again the value of z, right? And we have the solution for the problem as x1 equal to 20 by 19, x2 equal to 45 by 19 with z equal to 235 by 90. So this is the optimum. Now one takeaway is in simplex algorithm, as you can see, with every iteration, you're getting higher and higher values of z. You're not getting random values. So the simplex gives you progressively better solutions. And one thing you can figure out is that the increase in the z from iteration 1 to iteration 2 can be given by the highest Cj minus Zj into theta minimum. So 5 into 2 is 10. Right? So 5 into 2 is 10. So the increase that we see is here, 10. The next increase would be 1 into 45 by 19. So if we see 10 plus 1 into 45 by 19, that should be 190 plus 45 by 19. That should be 235 by 19. And so we have it. This is the simplex algorithm.